about inverses, if you keep in mind what an inverse does, it will help you get a perspective on your logs. We're going to do them graphically. We're going to flip them back and forth from exponents to logs. We're going to look at them in your calculator and all different ways to work with logs. But the most important thing is that logs are exponents. They're just inverses. Logs are inverses of exponents. And by saying this, an inverse is a reflection over the line y equals x. And when we do an inverse, a true inverse that passes a one-to-one function test, it passes a vertical as well as a horizontal. We look at our exponential curve and we say, yep, this passes a vertical and it passes a horizontal line test, so it does have a true inverse. And when we reflect this guy, when we reflect it, it's going to actually be its reflection like this. And this is where our log comes from. And because we interchange the x and the y, everything will interchange. The domain, which was the x values, will now become our y, our range for our logs. Our range, which was our y values, will now become our x, our domain for our logs. So we're going to interchange all these things. One of the biggest things is going from exponential to log. For instance, if I want to take 2 to the third and I want to write this as a log expression, okay, the one thing to remember is the base of the exponent function is equal to the base of the log. Okay. It's equal to the base of the log. Now, I don't care if you learned that. I don't care if you learned, well, log equals x. I use log equals exponent. Some kids learned that. Some learn log equals exponent. Whichever you're comfortable with will work for you. The one thing that we try to do is remember the rules of inverses. So let me I do log equals exponents. Mine, I think, is easy. If you like that, that's absolutely fine. I'm really not too keen. I don't know how to do it as well, but I do this. So I say my log, I line this up, I take my log base, my exponent is 3, and I could swap it out to a log. Now, way back when I was in school, if you take a look at this statement, and this always made sense to me, in college, I had a professor one time that said, easiest way, cover this guy up. 2 raised to the third equals 8. Easiest way. And it makes sense. So when you're going back and forth, if you don't like that, if you don't like log equals exponent, this raised to this equals that. And it makes sense. We can flip back and forth between logs and exponents because logs are exponents. They're just inverses. A log actually in base 10, your log in your calculator is actually base 10, your log key. But in base 10, we don't always write the 10, so we just say log. So if you're looking for the log of 100, the log is really the exponent. In scientific notation, this number is 1 times 10 squared. So since we say log equals exponent, the exponent here is 2. So the log of 100 is 2. It is its exponent. Only in base 10, which is what your calculator does when it says log. It does base 10. If we want to do a different base, we change the base. We convert it to a base 10. But if I take the log of 1,000, what should that be? What would the exponent be when I write this in scientific notation? 1 times 10 to the what? Third. So should this say 3? Try it. Try it in your calculator. What does the log of 1,000 say? The log is the exponent. It says 3. In base 10, it is the exponent. Okay? So flipping back and forth, sorry. Flipping back and forth, we have to remember to interchange the x and the y's. This is very, very important because a true inverse is a reflection over the y equals x line. So if we took this and we want to flip this to a log, we interchange the x and the y first. And then you can use your log equals exponent rule, whichever one you want to get to that. I find it easier to look at the numbers rather than the letters, because the letters don't make as much sense as when you look at the numbers, because 2 to the third, yeah, I know, that means 8. And then if I do this in my calculator, log base 2 of 8, I'll find it to be 3. Did you guys use the log base key to do this? Okay, so you guys are at a nice advantage because over the years, they came up with, and now the 83s don't have this, just the 84s do. There's a key in here, and you can get to it a number of ways. Alpha window, alpha window, and it's number 5, or you can go to, well, that didn't work out very well there. I don't know why that didn't work. Try this instead. It allows you, and I don't know if you can see it as well back there, it allows you to put your base in other than 10. So if we put our base of 2 and said 8, we would get our answer to be 3. Another way to do change of base, especially if you're using the 83 calculators where you don't have this, is to change the base yourself. On this guy, and it's very, very simple. Draw a line like this. Leave that guy below the line. So you say log base 10 of 8 over log base 10 of 2. So if you put this in your calculator, log 8 divided by log 2, you will also get 3. So those of you that have the 83 calculators, you're going to have to do it this way. I'm almost positive you guys don't get that log base thing. The same with the summation guy. Well, over the past few years, the Regents has allowed us to use those. We used to all have to block them out of your calculator, so sometimes you may grab a calculator that has a line through it, and I just have to reset it. But over the past couple of years, they allow us to use the calculator for that. It's just a way to calculate it if your base is not 10. So when we do this, and we say log equals exponent here, it might be easier to put your thing around like this. So your log base A, there's your exponent, x, then you can flip any of them around. If you use that, continue to use what you're comfortable with. If you don't know either one, use log equals exponent. It's really a good help. So that's our moving from exponents to logs and things like that. We're going to look more at this. For instance, this guy. I want to know, what is this answer if I take log base 2 of 32? If you want to flip this to an exponential, you want to change to exponential, set it up. Log equals exponent. What's the base of this log equation? 2. That's the base of your exponent. What's the exponent? Y equals 32. Now, to solve this algebraically, we drop this guy down to a base 2 to probably remember doing this. Once your bases are the same, then you can set your exponents equal to each other. If we ask for it algebraically, that's what we want. If you put this in your calculator using your base key, and you do log base 2 of 32, and you hit enter, you get 5. If you change the base formula like this, log base 10 of 32 over log base 10 of 2, you get 5. So it depends which way you want to go through this. We can change your base, we can put it in your log base thing. This made life a lot simpler using this log base. Sometimes we'll flip them to exponential equations. And if it says algebraically, you're going to have to flip exponential. I want you to be aware, though, sometimes you hit this. So we say 4 to the x equals 8. So we have to drop this down to the same base. So can I drop 8 down to a base of 4 with an exponent? 4 to the what power gives me 8? Nothing. 4 times 2 gives me 8, but not anything to a power. So in this case, I have to bring them down to a common power. 2 squared times x, and 2 to the third. Once they're in a common base, then I could set the exponents equal to each other and find out what my x was. Remember doing that? This we did a lot in Algebra 1. I'm sorry, Algebra 2. I don't think they moved it out of Algebra 2 yet, the logs, thankfully. Again, just to have some properties that you need to just see if you can kind of, don't memorize, but kind of just acquaint yourself with them. Again, we were just showing that these are properties. Any base of 1, log base 2 of 1, log base 10 of 1, log base 11,000 of 1 is 0 because a to the 0 power is 1. If you flip it around, you'll see that these are just properties. They make sense. Base e works the same way. This is your natural log over here. Before the break, we talked about your natural log. And we said your natural log is very, very close to a base 3 log. It's just a natural log because no matter what x goes to, it reaches the same number, 2.7812, whatever the number happens to be. It's a very close, and it has the same characteristics of a base 3 log. But remember that they don't show this base. Just like with a log, if I say this is still base 10, if there's no base on that log. So a to the 1 equals a. It just is a property. E to the 1. The one you'll use the most is this guy right here. ln and e will always negate each other. And we'll just drop that exponent down. Technically, we can do this because your exponent comes down. And again, if you have an x and y, remember we can always put logs on both sides or take logs away from both sides. When we go to work on your equations, we use that rule a lot. Our basic reason for using logs is one of these reasons. I can't drop 7 down to a base of 2. So how am I going to find out what x is? The only how I can find this out is if I can get this to come down. And the log lets me do that. Whether I take the log of both sides, or I take the ln of both sides. Now, when we get to the rules, we can bring this down. And then divide both sides by log of 2. And find out what our exponent was supposed to be. So that's one of our big reasons for using logs. Because I have no way to find that out otherwise. And we don't do guess and check. We could kind of figure, yeah, it's got to be a little bit bigger than 2, but not quite 3. It's not quite, I can play around with it and see how close I get to it, but we don't guess and check. So just kind of acquaint yourself with these rules, with these properties. It'll make life easier when we go to use them. I threw that in there for you. Yes. Yes. Another thing we do with your logs are we graph them. Now graphing, again, same rules. It's a reflection in the y equals x. So everything that we have here is going to swap out. So do this with me. This side is your exponent side. This side is your log side. So we're going to use your interchange rule to graph this. First thing I'm going to look at is my exponential graph. I'm just going to plug some values in here. So a -1 causes me to take the reciprocal. not to be a negative. Anything to the 0 power, 1. To the 1, 2, and 2 squared, 4. So if you recall before the break, whenever we graphed an exponential function, it kind of had this pattern, right? And what did we say our domain was? All real numbers. What did we say our range was? 0, good. 0 to infinity. We had a y-intercept of 0, 1. And what was our natural asymptote here? What is 0? X is 0 or y is 0? Not x is 0. We want this line, right? We want our x-axis. So what y value is that? 0. Right? Isn't that my y equals 0 line? I can't touch 0. In other words, there's nothing I could put in for x that will give me a 0. Try it. There's nothing 2 to the x power that you could put in for x that will give you a 0. All right? So now, we're going to use our interchange rule and find our logs because essentially logs are exponents. And like this, I can't put that on. Right? So logs are exponents. So now we're going to interchange everything. We're going to use our rule. We're going to swap these out. So for my log side, it becomes 1/2 negative 1. It becomes 1, 0. 2, 1. And you just need another box here. Sorry about that. 4, 2. When we graph this guy, it's going to look like this. Characteristics will always kind of be the same. It's going to go like this. It clearly shows us a reflection in the y equals x line. See it? We just interchange the x and the y's. Now the nice part about this is, when we did a domain, that was our x values, right? Well, we just interchanged it. This became our y value. So your domain becomes your range. And that looks pretty much like our range, all real numbers, right? Your y's now become your x's. So this becomes our domain. And here's another little tricky thing. X and y interchange, so that instead of a y-intercept, we're going to make this guy say x. We have an x-intercept. We're going to swap those values around, and we have a common x-intercept at 1, 0. Everything interchanges. All the x's become y's. All the y's become x's. And your asymptote, instead of a y equals 0, should be what? If we replace a y with an x, we get x equals 0. And isn't that my y-axis instead of my x-axis? They swapped around. So a true log, a true inverse, says interchange your x and your y's. And this will give us our characteristics of our logs. Regardless of what base we have, it follows the same pattern. Now, when we did your exponential curves, we said, okay, 2 was probably the widest. As it got higher, it hugged your y-axis. So as it gets higher, it's just going to hug your x-axis a little bit more. But we sketched them the same exact way. So we talk about using a calculator. We talk about converting them to exponential functions. We talk about graphing them. And even with these guys, we do transformations on these as well. We do transformations on your logs just like we do transformations on anything else. Now, I gave you the transformations for this, and one of my reasons in doing so, even though they follow the same transformation rules, I find these look a little bit different. And I caught a couple of your comments like I never saw these before. You did them. They just look a little bit different than they normally do. So for instance, a vertical translation. If I had this, and I vertically translated my parabola, it would look like this, right? When I shift my parabola up 2. Well, when I do my log statement, it looks the same way. There's my core graph, and when I shift it, it just says, shift this guy up 2. Bring me up 2 units. It's the exact same thing. They just look a little bit differently when you're looking at it with a log by it. But this has the same effect that this guy had. So when we're inside of this parentheses, it's the same as when I do this. Where's my transformation in my squaring function if I put it in by the x? Am I horizontal or vertical? Horizontal, and don't I go the opposite way, right? So same thing. I look for this parentheses and I say, oh, horizontal shift 1 unit right. I follow the same rules. Same exact rules. We start with your core graph. Log base 10, it just kind of hugs the graph a little bit closer, but we're okay with just making a sketch. We talk about your regular attributes, domain, range, x-intercept this time, and x equals 0 as your asymptote. Okay. When we do your transformation and we shift this guy 1 unit to the right, this little 1, 0 is going to now be 2, 0. It moved to the right. The horizontal shift when we did an exponential curve had no change, right? Because we were all real numbers. But a horizontal shift here has an effect because that all real numbers was now our range, not our domain. So with this, we take your domain, we add 1, we add 1, we add 1. So my new domain will be 1 to infinity. My range is not affected here. My new x-intercept will be 2, 0. And my new asymptote will be x equals 1. It has the exact opposite effect that it did on your exponential curves. Your exponential curves, a horizontal shift had no effect on it. But we interchanged your x and your y. So now a horizontal shift will have an effect on this, and a vertical shift will not have an effect on this. Because they're interchangeable. I gave you this so that I was kind of hoping you would see the difference. I know sometimes they're a little bit more difficult to see when we use the log words. A little bit more difficult. You guys okay with this? Okay. Let's try another one. My room is falling apart. Okay. Now, let's go back to a squaring function. So we did this. And do you remember me telling you that you could take the plus 2 instead of putting it here? Just move it over here. So where's our shift going to be for our squaring function? Two. Uh-oh. 2 up. Because it's not next to the x, it's away from the x. So same thing here. Put this over here. Where's your log function going to go? Up 2. So it has the same exact effect. Here's my log. Here's my domain. Started exactly the same as we did before. Here's my x-intercept. Here's my asymptote. So now, I'm actually shifting this 2 units up. I'm moving this guy up 2. And I'm doing the same thing here. Did I change my domain on this? Nope. Did I change my range on this? Nope. My range was all real numbers. So this is the opposite effect as my other one. So I didn't change any of these guys. I just moved everybody up 2. What I did change was my x-intercept. I changed my x-intercept. Now, to find an x-intercept, algebraically, you have to set y equal to 0. We didn't find a y-intercept because we have none right now, because we have an asymptote here. So if you go to this guy, and you solve for x, isolate your log, subtract 2 from both sides. Okay, if it's easier, and I find it easier to put this on this side, so log equals exponent, base 10 to what power equals x. So this just takes its reciprocal. So here's my x-intercept. Now you can confirm this on your calculator. I'd like you to get used to doing your transformations without your calculator, but if you want to go back and confirm this on your calculator, be my guest. We're log base 10, so you just need to say log of x plus 10, plus 2, sorry, plus 2. Now, oops, let me do it in 6. Okay, again, your calculators don't do a great job. If you have the color one, the color actually brings the line all the way down. But these guys, they kind of look like they stop short. If you're looking for an x-intercept, there's your zeros. So if you do second and you look at your zeros, start it from 0 and go to like 5, whatever, you should be able to see this guy. There's your 100.01. There's your intercept. It looks like it's sitting right at that axis, but remember, it's coming down using this asymptote as a guideline, getting as close as possible. We had the same problem when we did your exponential curves, because your exponential curves on your calculator did not get that close over here. It always looked like it stopped there, but it didn't. So the color ones are a lot nicer when it comes to that. We have kind of make those. So we're going to say this has a vertical shift up 2 units. Okay? We're covering a lot here, but we're kind of just looking at logs overall. We can do them graphically. We can put them in your calculator sometimes. We can interchange them back into exponential functions and solve them that way. We look at them as true inverses. So all your inverse rules apply. Your x and your y swap out. And we could do your transformations on them. And I really like you to do them without your calculator so that you could see where it's going. Questions? I apologize again for that noise. So one more thing, and that's looking at your domain. Okay, let's look at this graphically first. Don't forget ln and log are the same thing. ln is just a natural log, but it follows the same characteristics as a log base 3. So my graph of my log still goes like this. Still set, domain, range, negative infinity to infinity. Okay? Now, What would be my transformation when it's next to the x? Horizontal, which way is it going to go? To the right. Very good. So, easiest way is to figure this 0.10, add 2. Now you're at the 3, 0. So it's going this way. So we noticed we moved our domain. We added 2. We changed our intercept. We added 2. We moved our asymptote. We added 2. So our new domain is 2 to infinity. Our new x-intercept, 3, 0. And our new asymptote, x equals 2. You can't use 2 in this. You can't take the log of a 0 or a negative number because of where that asymptote is. No, it's an x value. Your y is this way. It's the y-axis, but it's an x value. We originally started at the y-axis, but it's at the y-axis, x is equal to 0. So it's a line that's going to go like this, a vertical line. Remember, we swapped it out. It used to be horizontal, but we swapped it. Now, because we see what's going on, that you can never take the log of a negative or a 0, we can kind of use that rule and bypass this a little bit. Remember when we used to do a radical, and we would say, what's the domain? We would take this and say x plus 1 greater than or equal to 0, right? Because we couldn't have a negative under our radical. Well, we can take this argument and set this greater than 0. Your domain has to be greater than 0. It cannot be 0 or negative. So now if I add 2, oh, look at that. Here's my domain, 2 to infinity. We can find our domain algebraically as well. Because your domain for a log has to be greater than 0. It cannot be 0. Try to put in a log of 0. It won't do it. A log of a negative number. It won't do it. So we could do it this way as well. And we can kind of confirm it with the transformation. That it works that way. It's easy. Okay?